Okay, section 11.2, chords and arcs. But what is a chord?
A segment whose endpoints are on the circle.
Nice job. Nice job reading. So let's see if I have, put my circle in here. Well, oh, whatever. Okay, so it is a segment whose endpoints are on the circle. So if I put a dot, and I name them, I don't know, P and Q, and we can name the center O. The center is always O, right? And connect them. That's a chord. So this thing right here, you can say is a chord. It's spelled like the chord on a piano or on a guitar with an H. So it's not going through the center, right? So the endpoints of it are on the circle. It's a chord. Usually, I should say, it's not. It doesn't go through the center. It can technically. Okay, so there's a theorem that relates to chords. There's 3 parts to the first theorem. I'm going to scooch up. I'm going to try and squeeze it all in here. So let's see. Within a circle, so inside of this, or into congruent circles. So within a circle, or in congruent circles, there's 3 things. 1, congruent central angles have congruent chords. Congruent central angles have congruent chords. Right? Mm-hmm. The second part. So, but first, let's make that make sense. What does that mean? Congruent central angles. Do I have a central angle in this diagram right now?
No.
No, I don't.
Wait, central angle.
A central angle. It's from the center to the edges. So let's just make up some x degrees. If I have another one that's like over out this way, and this is also x degrees, that would mean that this chord is congruent to this chord. That's what that's saying. Okay? Part 2. Congruent chords have congruent arcs. What is an arc?
Is it that part?
Yeah, and Annalise is pointing to, let's see if I can change the color even more here. Annalise is pointing to this part. So this is an arc. So congruent chords, the black lines, they're congruent. Therefore, these are also congruent. So if I go and label, I don't know, PQ, we'll say R is down here. So you would say arc, PQ. Yeah, that's an ugly Q. Q. Yeah. Q is congruent to arc, PR. That's what that's saying. The third part. Congruent arcs have congruent central angles. So, since the above black statement is true, since this is true, we could also say angle POR is congruent to angle POQ. Right here. These two are congruent. So, basically, if you have central angles that are congruent, you have chords that are congruent. If you have chords that are congruent, you have arcs that are congruent. If you have arcs that are congruent, you have central angles that are congruent. It kind of brings you a full circle, right? So if you have central angles, so coming back circle-wise, congruent central angles, you have congruent chords. If you have congruent chords, you have congruent arcs. If you have congruent arcs, you have congruent central angles, and back again. Like a nice little circle, you could just keep going and going and going. Yahoo! Let's try and use this. So example 1. In the diagram, circle O is congruent to circle P. Given arc BC is congruent to arc DF, what can you conclude?
They've got congruent arcs.
Hold on, I gotta draw it. Okay, so let me have some triangles in here, circles I mean. So, no, get back over there. Okay, and then we have 2 congruent circles. Yay. And we're going to label them circle O and circle P. and then there's some radii drawn in here like this, and then there's a chord across there like this, and then there's some points B and C, and in the other circle P we have similar stuff going on. We've got a radius, and you have point D and point F, and if I draw then in that chord, what can we conclude?
You've got the angle and the segments congruent also then.
Okay, so I could say angle O is congruent to angle P. Angle O congruent to angle P. What else can you conclude?
You got the segments, so DF and BC.
DF is congruent to BC. Anything else?
Well,
They already
said
gave
the
us,
arc,
right, they
yeah.
already gave you the arcs. So of these three things, they're all checked off.
Yeah.
So, great, we have congruent segments, the chords, we have congruent angles, and we were given this is congruent to this, the two arcs. Okay? Not so bad? Alright. The following theorem shows a relationship between two chords and their distances from the center of a circle. Let's try this one. So within a circle, or congruent circles, again, within a circle or in congruent circles, there's two more things that are true here. Chords equidistant from the center. I don't want the dice eraser. Chords equidistant from the center are
Well, isn't that
congruent.
always, like,
Yeah, not pi.
if it's equal distance, it's going to be congruent. Like, with no matter what it is.
Nah, no matter what it is, no. Okay, well, I'll draw this and I think you'll see. Then you can also say congruent chords are equidistant from the center. Okay? All right, so we have a proof of this. So like, I'm gonna draw a quick picture of this, and then I'll do the proof quick also. So chords that are equidistant from the center are congruent. So in other words, if I have something like this, where that chord, and here's the center, and then let's just say it's x distance away, and we remember we measure distance that's perpendicular. And if I have this one and it's also x distance away, it's the same distance, that means this chord and this chord, the whole thing, are congruent to each other. That's part one. But I can do the opposite. If the chords are congruent, then they are equidistant from the center.
Mm-hmm.
Okay? So let's get rid of all this and do a quick proof. Okay? So given circle O, segment OE is congruent to segment OF. We'll draw this diagram in a second. And segment OE is perpendicular to AB. Segment OF is perpendicular, good grief, perpendicular to CD. We need to prove that segment AB is congruent to segment CD. Okay? Yeah. Okay. All right, so our diagram. We need a diagram for this, right?
Mm-hmm.
So let's get a circle in here. I'm gonna make it a little smaller. Stick it over there. Okay? We have a chord somewhere about here, let's call it, and we'll say A, B. And somewhere maybe over here we've got chord C, D. And there's the teeny little center, so I'll make it bigger. We'll call it O. And if I connect C to O, D to O, B to O, I intentionally did not make them vertical angles. I wasn't trying to go for that. They're all a little off center there. And then we have this, which they said is perpendicular, and this, which they said is perpendicular. So we have the, I didn't name these points, F down here and E up here. So in the given part, we have given circle O, great, got that in the drawing. We have OE, that's here, is congruent to OF, right there. OE, the first one I highlighted, is perpendicular to AB. OF is perpendicular to CD. So this is the information we know so far. So where can we go from here to prove that these highlighted lines, AB is congruent to DF? Where can we go? Let's talk through it real quick. Look at the drawing. That should give you some clues.
Wait, AB?
AB, the chord, is congruent to the other chord. That's what we're trying to go for.
You mean CD?
Yeah, AB here is congruent to CD.
Oh, okay.
Oh, you kept saying or DF.
Something
I
else,
didn't say
don't know.
DF.
You should go and see. I'll get
I
a piece
will.
of candy.
Okay, maybe. All right. So we're trying to prove that those two chords are congruent. How can I do that? What two shapes do you have?
Triangles.
Do you have two triangles?
They both have right angles.
Okay, sure, they both have right angles. So I'm going to use purple, and I can go back and get rid of all the purple after we're done talking and actually write it out. We have two triangles. What is this called from here to here?
Radius.
A radius. So you have that.
And you have another radius.
You have another radius.
And another radius.
And another radius.
And another radius. So R
What
equals
do you-
R equals R equals R.
Oh, so this and this and this and this are all congruent.
Yeah, yeah.
Okay. What else do you have?
You got your right angles?
So
Yeah.
we know from the given, not wrong thing. I want to look at this one. So here, I'll go back and get rid of it. This one. Ah! No, that's not what I want to do. Right, what am I undoing? I don't want to keep undoing. Okay. This one is what I'm looking at. This is congruent to this, right?
Mm-hmm.
What kind of little triangles do you have in here?
Right triangles?
You have little right triangles. We have a hypotenuse and a leg. We have a hypotenuse and a leg. Do you remember anything special about hypotenuse and a leg theorem?
You have the HL theorem.
Yeah, the HL theorem. So this triangle here is congruent to this triangle here.
Yeah.
But wait a minute, aren't these two congruent?
Mm-hmm.
And this and this and
So you got
So
the
you
we have lots of triangles that are
side,
congruent.
side, side.
Not side side side. We have
Side and side.
hypotenuse leg. Hypotenuse leg. That's what we have to prove the little triangles are congruent to each other, right?
Yeah, or you can do that. Those angles are also equal to each other because they're flipper or whatever those things.
They're
are.
not vertical angles. I intentionally drew them so they're not vertical angles.
Okay.
So let's kind of get started. I think we have enough to go on here to start making some statements. So normally we start with the given. I'm going to save a little bit of space and not necessarily. I'll go back to the given in a second. Start with what we said about the purple lines here. And I need to erase some stuff because it's really
Purple
messy.
line.
Well, you can say
Just
all
gonna erase.
radiuses are congruent.
Ah, okay. So let me get rid of some things here still. All right, great.
also the
So
reason.
say, yep. Segment OA is congruent to segment OB, which is congruent to segment OC, which is congruent to segment OD. Center to edge several times. So the reason is that the radii of a circle are all congruent, right? Radii of a circle are congruent. Okay, great. So I can put that in my diagram to remind myself. We can say that OE is congruent to OF. That was given, right? OE is congruent to OF. And OE is perpendicular to AB. Same thing with OF. OF perpendicular to CD. And that's all what?
Given.
Given. Okay. We know that these are right angles, right? We said that right here, but we didn't say they're right angles, so we can say angle AEO and angle C FO are right angles. That's just definition of perpendicular segments, right? Four. So triangle AOE is congruent to triangle CFO. Let's highlight those. I need to change colors here. Something there, sure. AOE is congruent to CFO, right? Okay, I have two congruent triangles. I'm going to shade them in so I can really actually see them well. These two triangles are congruent. Why? How do I know?
Because of the HL theorem.
Yeah. HL theorem. Five. Since I have two congruent triangles, can I say that this angle and this angle are congruent?
SCP-CTC.
Yep. Angle A is congruent to angle C by CPCTC. Corresponding parts of congruent triangles are congruent. We already said this. Oh, I didn't mean to do that. This and this are congruent. The radii are congruent, right?
Mm-hmm.
So I can say that A and B are congruent, can't I?
Mm-hmm.
Why?
Because of the side
Angle B
angle.
is congruent to angle A, and angle C is congruent to angle D.
Wait, say that again.
Angle
B.
B is congruent to angle A. Why? What kind of triangles are they?
Right.
No,
It's a
isosceles triangle. Isosceles triangle theorem. Okay, so because of all that, we already said that, I switch colors here, angle A is congruent to angle C. But in the next line down, where I just underlined it, A was congruent to something else, and C was congruent to something else.
So by replacement or
Transitive, yeah, what? What do you want to say?
is that a trend?
Angle B is congruent to angle D. Transitive. Transitive property. And then the
Wait, we
last
did
what?
Angle A and C are congruent, B and A are congruent, so how can you add in B and D?
Look over here. Look where I'm pointing. So we already said A and C are congruent. Well, here's A, here's C in two separate statements. There's like a little line. Like
And B
semicolon.
and D.
So A is congruent to B, C is congruent to D. So I could replace in this statement, D could go in here.
Oh, I
B
did
can
not
go into
write
there.
C is congruent to D.
Oh, well,
Where
you
is
should
that
have.
at? Is that 5?
No, number 6.
6, I
Yeah.
have A and B.
And C and D. You have both. You need to have both at least. So now I can, in my diagram, I can add in that. All those base angles of the isosceles triangles are congruent. Okay, so what can I say about AB and CD?
There.
We've already proven the legs are congruent.
So you have to prove
We've already
those
proven the base angles are congruent.
So you have to prove those are congruent.
What?
The A, B, and C, D.
We can though.
Yeah.
Yeah.
Because what?
You combine those two.
What do we
like,
know?
in order.
Oh wait, so 8. What do we know about? Let me change colors so we can see it better. Yeah, red. What do we know about this angle and this angle?
Transversal?
No.
No.
Nope.
They're equal though.
How do we know they're equal?
Congruent, because we already proved the other stuff congruent, so they have to
Okay,
be.
so I can say angle AOB is congruent to angle COD. statement 8 is because if two angles of a triangle are congruent to two angles of another triangle, the third angles are congruent, right? We already said these two are congruent to these two, therefore the remaining third triangles have to be congruent. If two angles of one triangle are, you can check that out for me. If two angles of one triangle are congruent to two angles of another triangle, then
Can you say angle and just leave it?
yeah, you could. The third angles are congruent. I'm trying to squeeze this in so I don't have to scooch up and not see what I'm writing here. Last statement, if that's the case, you have congruent central angles. If you have congruent central angles, what can you say?
AB is congruent to CD.
Why?
They have congruent central angles.
Okay, so since Hannah's a little bit muffled, I'll say it for her. Segment AB is congruent to segment CD. And she said, because if you have congruent central angles have congruent chords. That was what we just learned in one of those theorems, right? Okay, got it?
Mm-hmm.
Great, now we can finally do example 2.
Yay.
I know, you're so excited. Example 2, find the value of A in the circle. Find A. Let's get a circle going here. Okay, there's our circle. From the center to a chord. The chord is going to be P, R, and with this distance drawn in here, it's going to be Q. And then we have another chord over here that's labeled A, distance long, we don't know. And we have this given to us. And we have that given to us. And we have this, and this is 12.5 units. And this is 9 units, and this is 9 units. Okay, what can I figure out?
Well, because QP equals is congruent to QR, they
QP
both
equals
equal.
QR.
Yeah.
Oh, right there, yeah, so I could write in 12.5 point. Okay, so you know that
But
much,
that's already given there.
which
Yeah.
equals 12.5. Okay, so now what?
Wait, what are we trying to do?
We're trying to find the value
Oh,
of A.
A,
So
okay.
if I highlight what
Well,
we're trying to
isn't
find.
it just 12.5 plus 12.5?
Basically, so but remember, we have this and this are congruent, so they're the same distance from the center, right? The two chords,
Yeah, so then this distance must be the same, and since this is circle, it
Yeah.
would be that.
so the two chords here and here are the same distance from the center, because
Which
that
means
was,
that they're the same length,
right. So if you can figure out this part,
which is 25.
which would also equal A, right?
Mm-hmm.
So segment addition process says PQ or QP plus QR, which would give you PR. So that was 12.5 plus 12.5, which is 25, right? So 25 equals PR. PR equals A must equal 25 also. Okay?
I think that's a complicated way to say that.
It is a complicated way to say it, but you can tell me. That's my. That's my.
way possible until the end.
No, I don't mind if you know this and you know this, therefore you can double it and tell me that part. I don't mind. I'm showing you the explanation. So in problems where it says explain, this part here is all of your explanation. Okay? So if you're asked explain your reasoning, how do you know that whole prove it? Right? That's the prove it part.
Bro, just look at it.
All right, 3 more theorems. There's so many theorems in this section. It's kind of insane. 3 more, real quick. In a circle, a diameter that is perpendicular to a chord bisects the chord and its arcs. So if I pull in a quick circle again, plop it over here. So if I have a diameter and it intersects a chord, it's saying that this is congruent to this, as well as this one congruent to this one. The arcs are congruent. Okay, that's the first of the theorems. So this is actually 11.6 if you're looking in the back at ever. 11.7. There's no titles to these. In a circle, a diameter bisects. That bisects a chord that's not a diameter. Is perpendicular to the chord. So if the diameter bisects the chord, which is what my drawing is showing so far, then it is perpendicular to the chord. So that's this part. I'm trying to keep it color coordinated here.
This would not be true then? Because I just have a thing in it. So that.
You didn't draw your. Yeah, no. How the way you drew it, no.
But it didn't say it had to.
If you're drawing a chord, Hannah, and you draw, if you draw a diameter that is it starts out that is perpendicular. You didn't draw it as perpendicular. That first theorem we just did.
Yeah.
If the diameter is perpendicular to the chord. Okay, that's what you had to start with. That's the part you didn't start with. 11.8, third theorem here. In a circle, the perpendicular bisector of a chord contains the center of the circle. So in a circle, the perpendicular bisector of a chord, so it's basically everything we have here. This is the perpendicular bisector, it's perpendicular, of the chord, contains the center of the circle right there. So in other words, it has to be a diameter or a radius that's bisecting the chord. If it's a perpendicular bisector, then it's including the center of the circle. Does that make sense?
Yeah.
Okay. Let's try some of this. I'm going to skip over the proof of some of that stuff.
Yes, please.
All right. Example 3, last example for this section. Find each missing length to the nearest tenth. So, circle. So glad I did that circle. I have a circle. We're going to name it Circle K.
I wanted to name him Robbie.
You can name yours Robbie.
His last name be Keen.
Yeah.
Oh, L and M, you guys are crazy, and that's a radius, right? That's R. We don't know what the radius is, but we know that this is 3 centimeters. And we know that the diameter is 14 centimeters.
That's not the diameter.
It's not a diameter, I know. That's a chord.
You said diameter.
Did I?
Yeah.
Sorry, I didn't mean diameter. I meant that
Oh
chord.
no, I drew the diameter all the way.
Oh,
Okay.
you can leave it. It's not going to hurt to have it there. So here's my diagram.
Label it.
That's the information to know. How do I find R?
Well, 14 cut in half.
Ah, you want to cut 14 and a half. Why do you want to cut 14 and a half?
Because then you have a triangle and you can figure out.
Because we just learned that the perpendicular line that includes the center to there must be the perpendicular bisector. So this side over here has to be 7 centimeters. Okay, now how can I find R?
Basically, this Pythagorean theorem.
Okay, so
R squared.
A
Equals
squared
this
plus B squared equals C squared. A can be 3, B can be 7, C can be R. So I have 3 squared plus 7 squared must equal r squared. So 9 plus 49 equals r squared. So 58 equals r squared. Square root both sides. R is approximately what?
Root 205.
Or decimal to the nearest tenth, I think it
Sorry,
says.
14.6.
7.6.
Wait, 14.3.
No.
I typed this in wrong again. Keep doing this.
Ha, I
Okay,
was
so
right.
pay close attention to the directions. In this one, it did say to the nearest tenth. Some of you are still having a hard time remembering what nearest tenth means. It means keep only one decimal place and round it correctly. I keep making notes on all your tests about this stuff.
That's tough.
Well, the
buddy.
test we're taking, we just did.
Okay. Anyways,
It hasn't
let's try another one of
taken.
these. B.
Yeah, never told us instructions.
Part
so I'm
B.
just doing all to the 10.
Well, if it didn't say, then that's fine. I
I know.
can't. I
I
can't
just
hold you to
left
something
it.
that it doesn't say. If I
Oh,
wasn't
no.
clear.
You're doing me. You just do another one.
I am making you do another one. This
Me,
is called
you don't love
Circle
us.
B. I do love you. That's why I'm making you do another one.
That's actually probably pretty smart because, you know.
So we have this, and we have a radius, and then the information given, we'll still label point C, point A, and I think that's all we really need. So here's 11, here's Y, and here's 15. What can I figure out based on what I know here?
You're doing the same thing, just backwards. Yeah.
Kind of. What do I know anything about the segment CB and AC?
If I say another perpendicular.
How do I know they're perpendicular? It doesn't give me that. How do I know they are?
Because these are both.
Because it has to be.
Ah,
not
so
theorem learned.
this chord has been bisected. If it has been bisected, it had to be bisected by a line that contains the center. And it is a perpendicular bisector then, right?
Yeah.
Then you can use
Okay.
the Pythagorean theorem again.
Great.
No way. 15 squared equals y squared.
You are never going to forget the Pythagorean theorem, are you?
No.
No, I like this theorem.
Why
a
would
lot.
we?
It's fun.
So I have y squared plus 11 squared equals 15 squared. Y squared equals 120, not equals, plus 121 equals 225. If I subtract 121, I end up with,
10.2.
okay, but what's the before that part? 104.
What one are we?
I don't know.
Oh, root 104 to find y.
Right, yep.
10.2.
So y is approximately, and that should make sense, that whole common sense check. Square root of 100 is 10, but we're a little bit more than 100, so it'd be 10.2. Okay? Questions?
Even if I did, I would say no.
Good job, Lily. We love
All right.
you.
Thanks for joining us.
Have a nice life.